Hello everyone, I'm Maeghamala from EC Department, IARE, Dundigal, working as an assistant professor. So I'm here to discuss about the language elements which are present in the Verilog. So we'll go forward. Yeah. So coming to this particular presentation, we'll just recapitulate whatever we have discussed in the last class. So far we have discussed the language elements. There are totally 8 or 9 language elements that we have discussed. They are nothing but the keywords we discussed about. We discussed about the comments, discussed about the number specification, and we discussed about, under the number specification, we discussed about the sized and unsized numbers. Okay, and few examples based on what we have discussed on each and every lexical tokens we have discussed in details. And this is a continuation of the previous presentation, that is language constructs or else the language elements. So the language elements so far we have discussed is these are the language elements: keywords, comments, number systems, and categorization of the number systems with their examples and so on. And today's topic is about the string. So this string is also one of the language elements or else the constructs, the language constructs which we observe in the Verilog. So what are these strings? What are these strings? String is a sequence of characters that are enclosed by double quotes. So these are the sequence of the characters. So these are the sequence. A string is a sequence of the character that are enclosed by double quotes. And the restriction on a string is that it must be contained on a single line. The restriction that we have observed on this is it must be contained only, it must contain on a single line. That is without a carriage written. So without any written, it must contain only on a single line. This is one of the restrictions to be followed in order to implement the string construct. And it cannot be on multiple lines. So as the restriction is that it should contain only on a single line, but it cannot be on a multiple lines. So strings are treated as a sequence of 1 byte ASCII values. So the important point is they cannot be they cannot be on a multiple lines. They should be only on a single line, and also the strings are treated as sequence of 1 byte ASCII values. ASCII value is nothing but American Standard Code information. Okay. The third point says that here in strings, it cannot be on multiple lines, but the strings are treated as sequence of 1 byte of ASCII values. So here in the example, you see, they are enclosed by the double quotes, right? So here there is a word mentioned, hello Verilog world. So this is a string. Why? Because this particular sentence is quoted in the double quotes. And also you see here double quotes A/B. This is also a string. So the important point to remember the string is it must contain on a single line but not on the multiple lines, and also the characters that are enclosed must be in a double quotes. So this is all about the string. Coming to the data types. What are these data types? In the Verilog, particularly in the Verilog program, what are the data types? The data handled in Verilog fall into 2 categories. So the data types are divided into 2 categories. One is net data type and the other one is variable data type. So what is this net data type and variable data type? We will discuss in further. The 2 types differ in the way they are used as well as with regard to the respective hardware structure. So here, based on the hardware structure of a particular module, we can categorize what sort of data type that we can use. Okay, based on the hardware structure, we can sort out or else we can categorize what sort of data types that we can use, either net data type or variable data type. Okay, it's all depends with respect to the hardware structure that we are considering. Next, data type of each variable or signal has to be declared prior to its use. So here, before the usage, the data types of which variable, each variable or signal has to be declared. So the data type, the signal, particular signal or variable has to be declared before itself, before we go forward, or else before we move forward into the program. The data type of each particular variable and also the signal, it has to be declared prior to its use. Okay, so the same is valid within the concerned block or module. So here, if for suppose in this module, if you are writing any the variable, so in this particular module, if you are writing a very long program for this block, okay, so before writing block itself, you should mention what are the type of, what sort of data type it is. Okay, you have to be clear with what sort of data type it is. It is a net database or else a variable data type. You have to be very clear about the data types that you are going to use before you use it. Okay, so the same valid within the block within the blocks in the module. In the module, for each and every block, there are many blocks to be considered, right? So module, for example, if you are considering a complex digital circuit, if you are considering a complex circuit, in this complex circuit is made up of many number of blocks, right? So each and every block has its own specification, and all these blocks must be interconnected. So for each and every block, you have to mention what sort of data type what sort of data type we have to consider. Is it a net data type or is it a variable data type? All must be before going forward. We have to be ready with the data types, what sort of data types that we are using. So it has to be mentioned within the block and also within the module. Next, nets. What is a net? Net signifies a connection from one circuit unit to another circuit unit. As I said, if you are considering a complex circuit, this net signifies the connection from one circuit to the another circuit. So here you have many number of blocks: block 1, block 2, block 3, block 4. So what is a net? The net indicates the connection from one circuit to the another circuit, the connection from one block to the another block. This is nothing but the net, and such a net carries the value of signal it is connected to and transmit to the circuit blocks connected to it. So here it is saying that the net that carries a value of signal. So for this particular B1, it carries some value. Okay, B1 carries some value of a particular signal, and this value will be connected to B2, and it transmits from B1 to B2, B2 to B3, 3 to 4, 4 to 5, and so on. So the net carries, this is a net, the net carries a value of signal of one particular block that to be transmitted to the other block, other circuits, okay, which are connected to it. And if the driving end of a net is left floating, the net goes to high impedance state. So here what you can observe here is, if the driving end of a net is left floating, if you observe that the connection between the many number of blocks are present, and if you see that driving end of the net is left floating, if you observe the connection between 1 and 2 are present, and if you observe the information that is observed by B1, that is observed by B2, which is obtained from B1, and observed by B3, which is obtained by B2, observed by B4, which is obtained by B3. If you keep on without any pause, if you keep on the driving end of the net which is floating, if you keep on that floating, you see there is a chance of high impedance state. That means what? This complex circuit, it may go, the state of this complex circuit would be in a high impedance. Understand? This is very clear. Clearly this point is talking about, if you see a floating, a constant floating, if you observe in the complex block, if you observe in the particular module, you see there is a chance of the net which goes to a high impedance. The net which goes to the high impedance, that is we represent with Z. If there is a floating is high, if you see the floating is maximum, you see a high impedance value. If the floating is minimum, you see a constant output that you can observe at the output. But the floating is high, always remember the impedance value goes, you see the high impedance state, the particular circuit will be in a high impedance state. Next, a net can be specified in different ways. So there is a specification, there is a representation of how a net can be used. So we will see the net can be specified in different ways. Coming to value set or logic values. So this is one of the construct that you observe in this Verilog. So what does this value set or logic value indicates? So Verilog supports for 4 values and 8 strengths to model the functionality of real hardware. So if you observe this value set and logic value, this Verilog, the particular Verilog, it supports the 4 values, 0, 1, X and Z 4 values, and 8 strengths model for the functionality of real hardware. So the 4 values are listed in the table below. So here if you see, if you observe this particular table is showing us the different 4 levels and also the 8 strengths to a particular model. So here, so for the value level, you have 0, 1, X and Z, and the condition in hardware circuit. So what sort of condition that you can observe when the particular circuit observes the output with 0, output with 1, output with X and output with Z. So if the value goes 0, you see the logic zeros and it is a false condition. We all well known. This is a well known fact that when the value is 0, it is a false condition. When the value is 1, it is a true condition, logic 1, isn't it? And when the value is X, this is the unknown logic value. X is meant for unknown. In the previous slides we have discussed, in the previous presentation we have discussed what is X and what is Z. Okay, those two are the important representation in the Verilog modules for the unknown values and also for the high impedance state. So the same indication for the value set or logical values, we are indicating the same thing. Z is nothing but the high impedance or floating state. Okay, so in the previous slide also we have discussed what is this floating state and what is this high impedance. In the modules, in the circuits, in the digital circuits, if you observe the constant floating, then you will observe the output has high impedance. Okay, the maximum floating state is observed, the output is high impedance state. So these are the 4 values with the 8 strengths modules. That is nothing but the value set or the logic values. And here we see in this value set, we observe wire. What is this wire? It represents a simple wire doing an interconnection. Okay, wire indicates nothing but the connection between the blocks, connection between the gates. If you have 2 gates, 2 AND gates, okay, using this wire, you will be connecting to the OR gate, isn't it? That's how you'll get the output. If these are the inputs, using this wire, this is a wire. Wire is nothing but it acts as an interconnection between the blocks, or else it acts as an interconnection between the modules. So it represents a simple wire doing an interconnection, and only one output is connected to a wire and is driven by that. So here only one output is connected to the wire, and so from there it drivens to the other gate. So here from this AND gate 1, we have 2 inputs and we have 1 output. So this output acts as a wire. It is driven as input to the OR gate. This is the output actually, and it gives us input to the AND gate. So from there we get the output. So only one output is connected to a wire and is driven as the input to the some other gate. So this is an interconnection between the gates or else a modules or else a block. And what is try? Try is, it represents a simple signal line as a wire. So this try is nothing but a simple signal line. So the try, it represents a simple signal line as a wire. So what does it mean? Unlike the wire, a try can be driven by more than one signal's output. So what does this wire says? Wire says only one output is connected to wire, right? So this try is not like that as compared with the wire. It is something advanced which says that a try can be driven by more than one signal outputs. So more than one signal outputs. For example, there may be a chance of getting sometimes there may be a chance of getting more than two outputs, right? So in that case, we can make use of this wire. So this wire, it represents, it is a simple signal line as wire, but it can be driven by more than one signal outputs. And also, nets are 1-bit values by default unless they are declared explicitly as vectors. So what are these nets? Nets are nothing but they are the blocks inside the modules, okay, which are interconnected. The blocks or else the gates or else the flip-flops inside the digital circuits, if they are interconnected, and if they are interconnected by observing the output, this cluster is nothing but the nets, right? So the nets are 1-bit values by default unless they are declared explicitly as vectors. So by default they are 1-bit values unless if we are declaring them as vectors. Okay. Then the term wires and nets are often used interchangeably. So here in this particular language construct, sometimes we can use sometimes we may use wire, sometimes we may use try, or else sometimes we may use net. They are oftenly used and we can interchange also based on the output that we are observing. If it is a 1-bit output, we can use simply a wire to connect the different modules, to connect the different gates. Okay, if you are observing more than 2 or 3 outputs, then you can go for this try and also nets. So these the term wire and nets are oftenly, they are interchangeable. And coming to variable data type. What does this variable data type mean? So a variable is an abstraction for a storage devices. So this is an abstraction for the storage devices. We use variable. See, in order to write a program also, we represent the variables, right? We represent x, y, a, b. Okay, these are the variables that we represent. So these are the abstraction. The abstraction for a storage devices. We see number of variables we can see in the variable library of a Verilog library. So it can be declared through a keyword register and stores the value for a logic level 0, 1, x, z. So these are nothing but it can be declared through a keyword register. So register x. This is a variable. So the register x is a variable, and the variable, and we store the value of logic levels. We store this particular particular value that it contains in terms of 0, 1, x and z. Okay. So using a keyword register. So register keyword using the keyword register, we are storing a variable x, and that variable that variable indeed it stores the value 0, x or z, 0, 1, x or z. Any logical level, it represents the output, for example. That is, if x is an output, the output could be of 0. That means it could be of false, it could be of true, it could be of unknown, and it could be of high impedance. This is a variable output representing x. Okay, likewise we represent the output, for example, AND gate A, B. C is the output variable. A and B are the input variable. So this output variable will be 0 or 1 or 1 or 0. Okay, sometimes X or Z. So we store this variable, the output variable, using a keyword called register. Then a net or wire connected to a register takes on the value stored in the register and can be used as input to other circuit elements. So here this sentence is talking about a net or a wire. A net or a wire connected to a register, takes on the value stored in the register. So this particular register is having 0 or 1. This particular value can be used as input to other circuit elements. Understanding my point? See, for example, 0 and 1. Okay, here we observed as 0. This is, I told you, the register values can be stored in terms of in the logical level 0, 1, X or Z. For example, I got output as 0. Okay, I am assigning in this particular using a keyword register, and that particular register, it can be used as an input to some other circuit. So input to some other circuit. Likewise 1, 0. So this is 1. Here I have observed 0 and here I have observed 1. Okay, this acts as again as input to some other circuit, and from there we get the output as Y. So this is what the sentence talk about. A net or wire connected to a register on the value stored in the register and can be used as an input to other circuit elements. Okay, but the output of a circuit cannot be connected to a register. So we have to remember this, that the output cannot be connected to a register. Only the register is a keyword where we store that particular output information in it, but we cannot directly connect it to a register. Next, the value stored in register is changed through a fresh assignment in the program. So the value which is stored in this particular register, it can be changed through a fresh assignment in the program. That is time, in terms of time, real and real time, and all other variable data types. These are dealt with later. So not only with the register, we also have a variable called time, integer based on real time, and all other data types. These are dealt in the later session, but the main important, or else a main construct that we can observe in the particular Verilog programs is about the register, the keyword register, or else a variable where we store that particular variable in a using a keyword called register. And what are the scalars and vectors? So what are the scalars? Scalars are nothing but these are the entities representing single bits. Whether the bit is stored, changed, transferred are called scalars. So the scalars talks about these are the single bit representations, and they can be stored in bits, and those bits, whatever the single bits are there, they can be stored, interchanged and transferred. They are nothing but the scalars. Often multiple line carry signals in a cluster like data bus, address bus and so on. So here if you observe, there are multiple lines. The bus consists multiple lines. It could be either input or output from circuit 1 to circuit 2. If you take a large complex circuit, connection from one circuit with one thing is not possible. Okay, you see a complexity. You see all the wires will be messed up. So in order to make it as a free, we are using a bus. Okay, bus is nothing but the connection between the two circuits or the module. So often multiple lines carry in a cluster. Multiple lines carry in a cluster like data bus. So this bus could be a data bus, address bus and so on. Okay, next. Similarly, a group of registers stores a value which may be assigned, changed and handled together. So likewise, if you observe group of registers, the value which are stored in the group of registers, they can be changed. As I said, the first sentence talks about the bits are stored, changed and transferred. So likewise, if you observe a group of registers, even though the register has a many number of elements, and those number of elements are pertaining to 1 register, pertaining to 2 register, pertaining to 3 register, you see the group of registers stored the values, they can change, they can assign, and they can handle all together. Okay. Then the collection here is treated as vector. So here all the collections of the variables not only pertaining to 1 register, but also many number of registers, the values which are stored in many number of registers all together, you are calling it as the collection of all the registers are treated as vectors. The collection of only one single bit where it can change, where it can transfer, you're calling it as vectors. But as a group of numbers all together, bits in the form of register, you're calling it as a vector. This is a similarity. This is the difference between the scalar and the vector. Coming to the figure below, in the figure below, you see the difference between a scalar and a vector. We can observe. WR, write and read, are two scalar nets connecting two circuit blocks, circuit 1 and circuit. So in this particular figure, you see circuit 1 and circuit 2. There here, you have read, you have write. Read and write are the scalars. Okay. Read and write. For circuit 1 and circuit 2, there is a connection, there is a read. We can read the data and we can write the data. So this is nothing but these are reading and writing are nothing but the scalar bits. Okay. Coming to bit 0, bit 1 to bit 3. So here we have 4 bits. Bit 0, 1, 2, 3. So these 4 bits are nothing but the vectors. As I said, a group of numbers which are presenting in a register. Okay, for example, this register, I am naming it as P. I am naming this particular register as P. This particular register consisting of 0, 1, 2 and 3. Okay, this 0, 1 and 2 and 3 are the bits which are presenting in the register. So, I am calling this as a vector. But if you see individually, there is a read and write. So, I am calling it as a scalar. Okay. So, B is a 4-bit wide vector, net connecting the same blocks B0 to B3 and are individual bits of B. So, here it is a 4-bit. 1, 2, 3, 4, isn't it? You observe a 4 wire, it is a 4-bit block which consists of 0, 1, 2, 3. So, that we are calling it as a vector. For this vector 4-bit of B, we have 4 bits are present. So, we are calling it as a vector. They are part vectors. So, as these are the part vectors. Why 0 is a part vector of register B, 2 is a part vector, 3 is a part vector and 1 is a part vector. So, we are calling it as, for a part vector, B, individual vectors are called as part vectors. B0, 0, 1, 2, 3. Okay. So, this is a vector representation and these are the scalar representation. So, a vector register or net is declared as at the output in a Verilog program and hence treated as such. So, here a vector register, the vector register consisting of group of numbers all together combining as one. So, we are calling it as a net or we can calling it as a vector. Vector register or net is declared as outset in a vector program and the range of vector is specified by a set of 2 digits. So, the range of vector it could be a set of 2 digits. That means 0 or 1, 1 or 0, 0 or 0, 1 or 1. Okay. Or expression evaluating to a digit with a colon in between the 2. So, here 0, 1, 1, 0, 0, 0, 1, 1. This is how we represent the range of vector and the representation would be like this. Then the combination is enclosed within the square brackets. So within the square brackets, 0, 1, 1, 0, like this. Okay. Zero, 0, 1, 1. So this is how we represent the vectors. Example, if you observe here, we have a wire. So here, if you observe in this particular example, we are representing wire using wire, register and wire. So for this wire, 3:0. Okay, these two are the vectors in register A. So what does it says? A is a 4-bit vector. A is a 4-bit vector of net type, and the bits are designated as A are 3, right? So A3, A2, A1 and A0. So totally 4 bits we observe. That is in terms of wire. What is a wire? Wire is nothing but output would be observed only 1 bit, and that bit can be given as input to the other digital circuits. Okay. Coming to the register. Register 2:0 B is nothing but it is a 3-bit vector of register type. It is a net type. Okay. And it is of register type, and the bits are designated as 2, 1 and 0. See, you say this is a multiple line comments. When it comes to the comment, if you observe the comments construct, this is a multiple line. Multiple line comments, okay. Coming to 4:2 C. So C is a 3-bit vector register type, and the bit is designated as 432. 4:2, 3-bit, 432, 2:0, 210. It's a 3-bit. 3:0, 3, 2, 1 and 0. It's a 4-bit. Okay, it's a 4-bit. It's a 4-bit, 3-bit, 3-bit and -2 to 0. -2 means -2, -1, 0, 1 and 2. So this is a 5-bit vector with individual bits designated as individually. How we are designated? With D of -2, D of -1, D of 0, D of 1, D of 2. D of 2, isn't it? So totally how many bits? 5 bits. Totally how many bits? 4, 3, 2. 3 bits. Totally how many bits? 2, 1, 0. 3 bits. Totally how many bits? 3, 2, 1, 0. 4 bits. Okay, this is how we represent the scalar and the vectors in the Verilog constructs. So dear students, till now we have discussed all the language elements or the constructs which are present in the Verilog. So far we have discussed about the vectors and the scalars, the difference between the vectors and the scalars, and also the data types, variable data types. We see, like we have discussed about what is a wire, what is a trier and what is a net, and also we have discussed about the net delays, and we have discussed about the data types, the net data types and net data types and the delayed net data types. So far we have discussed about the data types. Under the data types, we discussed about the net data types and the variable data types. What is a net basically, and what are the individually what a net consists of, and also how it relates to the vectors and the scalars. And also we have discussed about the strings, how we are representing the strings using a single line or else in a double line, okay, in a multiple line. So this is all about the language elements in the Verilog. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.